To start this exercise, we first go into the tree of this simulation file that STAR-CCM Plus has prepared for us. If you go to the geometry section and then open the operations folder, you'll see that two operations have already been created as presets. The first one is the baffle/2D extraction type operation that's needed to generate a 2D mesh, and after that we have the automated mesh operation, which is the standard one we use for creating a 2D mesh. We already covered 2D mesh generation in the previous example and exercise, and we gained a basic understanding of how STAR-CCM Plus handles 2D meshes and 2D cases. So I won't go into those details again here. What we need to do now is simply run the automated mesh. Right-click on Automated Mesh, click Execute, and then give the file some time so that STAR-CCM Plus can generate the mesh required for this simulation. While the mesh is being generated, you can also go into the mesh settings and review them. You can see that polygonal mesh is selected, prismatic layers are enabled, and the base size is set to around 1 mm, i.e. on the order of 10^3 meters, and so on. Once the meshing process is complete, I can go into the Scenes folder and, for example, open the Scene 4, Volume Fraction of Oil. This is the main scene for this case once the mesh has been created, and you can see that now it is 2D. If I go back to geometry, you can see that the geometry has been converted from a full 3D solid into a 2D cross-section, essentially a plane. To actually see the mesh, I can, for example, stay here in the geometry scene and in the surfaces node. I'll bring this tree up a bit so you can see it clearly, and then I can scroll and find the mesh option. You can either click Mesh in the tree, or use the Show Surface Mesh button at the top. If I click Show Surface Mesh, these are the cells that have been generated for me. As I mentioned, the mesh is polygonal, and we also have prismatic layers near the walls. This is the geometry and mesh we are going to use to solve our problem. Before continuing, I'll save this file with a new name. The original file name was something like start, so I'll change it and save this one as gear_pump_run, meaning this is the case that I'm actually running and applying the physics to. The next important step at this stage is to review and set up the physics of our problem. The continuum I have here is called Physics 1. Right-click on Physics 1 and choose Select Models. By default for this case, the two-dimensional model is already active. That comes from the mesh and problem setup we just discussed. We also have Solution Interpolation active, which is used to interpolate the solution in regions where STAR-CCM Plus needs it. For the time discretization, in this example we want to solve a transient, unsteady, problem. So I select implicit unsteady as the time model. Next, for the flow regime, because we're dealing with multiphase flow, I need to activate the multiphase model. So under multiphase, I click to enable it. When I do that, STAR-CCM Plus opens another box where I can choose the specific type of multiphase model I want to use. The model I want to use here is the Mixture Multiphase Model, which is often abbreviated as MMP. Once I select the Mixture Multiphase Model, STAR-CCM Plus automatically adds the appropriate supporting models, such as segregated flow and gradients, because they are required for this mixture approach. For turbulence modeling, that is, to account for the turbulent viscosity, I have three main options. I do want to model turbulence, so I enable the turbulence model. Because this is a 2D example, STAR-CCM Plus automatically selects Thin/2D style options, and I choose the K-epsilon model. When I pick K-epsilon, the software automatically selects realizable K-epsilon, plus a wall distance model for the distance to the nearest wall cell center, and two-layer all-Y plus as the wall treatment. We've already used these options in a previous example. In STAR-CCM Plus, the default K-epsilon setup is the realizable K-epsilon model, which is more robust and accurate compared with the standard one. The additional wall distance and two-layer all-Y plus treatment help to properly handle the near-wall viscosity based on the Y plus value. Another model that we need to activate is gravity, because we want to include gravitational acceleration in our multiphase simulation. So I enable gravity as well. Now all the required models for this multiphase problem are selected. Click Close, and you can also hit Save now that the physics setup is defined. If I click on Physics 1 in the tree and expand models, I can see the full list of models that I've chosen for this case. These are all the physical models that will be used in the simulation. Next, under Mixture Multiphase, in the Models list, MMP, I right-click and select Edit. When I click Edit, STAR-CCM Plus asks me how I want to handle the transport terms for the multiphase equations, for example, which convection scheme to use and what reconstruction or accuracy level I want. For this example, for the convection term in the volume fraction, alpha, equation, I want to use adaptive interface sharpening. This option helps keep the interface between the two phases, the oil and the air, as sharp as possible. So I choose adaptive interface sharpening. After selecting that, the software provides additional options for this model. One of these is the number of cell layers, that is, how many layers of cells around the interface should be considered as the interface band. By default, this is set to 2, and I'll keep that default value. Click Close, and then save again. Another important point in this part of the exercise is that, since we are simulating a multiphase flow, we have to explicitly define the phases for STAR-CCM+. Where do we do that? Under Physics, there is a model called Multiphase, and if you expand its tree, you'll see a folder named Eulerian Phases. This is where we define the Eulerian phases used in this mixture model. By default, this folder is empty. To add a phase, that is, to add a material or fluid to the mixture, right-click on Eulerian Phases and select New. When I click New, the model selection dialog appears for the new phase. This will be Phase 1, the first phase that I'm going to define. To keep it clear, I press F2 on Phase 1 and rename it so I can remember what it is. And then set its properties. If I right-click on Phase 1 and choose Select Models, I can now define the material behavior for this phase. Because I already selected turbulent flow in the continuum, this phase also has turbulence enabled by default. The material type I want for this first phase is liquid, and I will assume it has constant density. If you wanted to add other models or properties for this phase, you could do that here, but for this example, I don't need anything more. Click Close. Now the first phase is defined. Next, I go inside the liquid material. By default, when you select Liquid, STAR-CCM Plus automatically inserts water as the initial fluid material. I click on Water, press F2 to rename it, it might appear as H2O, and change the name to Oil. Now if I expand Oil, I can set the material properties for this fluid. It asks for two main properties: density, dynamic viscosity. Because I set the density model to constant, I just need to enter a single value. For this example, the density of the oil is 880 kg/m superscript 3. The dynamic viscosity I will use is 0.02 Pa/s. These are the properties of the lubricating oil that I want to model in this gearbox example. Alongside the oil phase, I also need to add the air phase. So I go back to the Eulerian Phases folder, right-click again, and add New to create another phase. A new phase is added, I press F2 and rename it appropriately, for example, to Air. Right-click on this new phase, choose Select Models, and now set this phase as a gas with constant density. Then click Close. If I now go inside the material model for this gas phase, you'll see that by default STAR-CCM Plus assumes it is air, with its standard density and viscosity. So I don't need to change the density or dynamic viscosity for the gas, I can keep the default air properties for this example. With that, I now have both oil and air defined as my Eulerian phases. In the next part of the exercise, we will continue and set up the remaining parameters needed for this case.